Thank you. Okay, thank you all for coming. I want to preface the talk by saying that I have some good news and some bad news. The good news is that this talk is definitely going to be the most accessible one, because you don't really need much knowledge to be able to follow it. The bad news is just for me, because I guess if somebody gets lost, it's just my fault. But yeah, don't worry about that. Let's go. Okay. So from the title, you see that what I'm after is this kind of polynomials which are sums of powers of other polynomials. In particular, I'm looking for even powers of linear forms today. And the reason for that is mainly, I would say, because non-negativity certificates are extremely important. And also, what we can say is that you can, these kind of certificates are useful for optimization, and this cone is not only contained in the PSD cone, but also the SOS one. And often people go to the dual. The dual cone of this one is quite familiar. It's just consists of non-negative polynomials. And if you're interested just in non-negativity on a specific set, then you can also do that. And what happens is that you will only get linear forms that take coefficients in a kind of a subset. Okay, the subset where you have non-negativity. My plan for today is introduce you to these PSD Hankel forms, whatever they are, and how do they kind of link to the problem of decomposing polynomials. So the punchline is that these PSD Hankel forms are interesting because there's this problem, that there's this theorem that says that these are one of the possibly many types of polynomials that actually are decomposable this way. Okay, so bear with me a little bit for the definitions. I know it's not the best, but we will go through them quickly. So I'm only interested in real polynomials, no complex numbers now. We're just interested in the real numbers and homogeneous polynomials. And maybe many of you will know that considering only homogeneous polynomials is not really restrictive, because all these non-negativity problems and kind of decomposition problems can be stated just in terms of homogeneous polynomials. It's equivalent. Then we will have these multi-indices. We've seen them many, many times. Many of you have called them like partitions. And this k would be the height, if I remember correctly, from Alexander's notation. And finally, I introduced this other number associated to a multi-index, or equivalently to a term of a polynomial. Since I'm going to use these multi-indices to kind of express concisely powers. Okay, and so we have this kind of sum. So we sum up the indices, and there's this weight given by the actual index that we're considering. Okay, so let's start with the definitions. Definitely, many of you know the catalectical matrices of a polynomial. I'm only interested in one today. So since we're considering even degree polynomials, I can always build this kind of square matrix. And you see that the entry of the matrix is indexed by these multi-indices that give me like the powers of the terms. And clearly, I need to kind of order these multi-indices, and every multi-index is going to be just ordered lexicographically. Okay? And so we have this polynomial in X. Some of you definitely know gram matrices, and this is one example of a gram matrix of the starting polynomial. Associated to this matrix, we can construct a quadratic form. We just multiply on both sides of the matrix by this kind of set of variables. This is just like a kind of a substitution, because each variable corresponds to a different monomial in X of degree m. But this helps us see more clearly what I want you to see today. Okay, let's see just a quick example. What is an example of the largest catalectic matrix of a polynomial? I just put the monomials outside the matrix, so you see the indexing. They're ordered lexicographically, as I said, and so you can see this is like kind of the one is the index of this one, and then you kind of get the two, but you need to normalize for the multinomial coefficient, and you can kind of fill up this whole matrix. Okay, this is really standard. Let's go now and talk about Hankel forms. Okay, now finally this weighted index sum plays a role. So for a Hankel polynomial, we require that whenever two terms have the same weighted index sum, then we want them to have the same coefficient. And I don't know, maybe you're asking yourself, what does the Hankel name do? Like, where's the Hankel structure? And the Hankel structure can be seen more clearly if you think of the symmetric tensor that is associated to the polynomial. So you know that you have a homogeneous polynomial. You can also talk about a symmetric tensor associated to it. And then the tensor, what it's going to show is this really nice structure, which reminds us of Hankel matrices. Hankel matrices have constant antidiagonals, and this associated tensor kind of have constant, like oblique slices in some sense. Okay, but I'm not going to talk about tensors anymore. I prefer to talk about polynomials. In particular, you see that what really matters is this kind of finite sequence of coefficients that we can index with the weighted index sum, because the rest of the data is kind of redundant. And so with this kind of idea, we define a vector that is associated to a Hankel polynomial and contains all the information. And it's defined pretty much like this. You just put these entries, and you fill up the vector. Now we can finally talk about what the PSD Hankel forms are. We need to use this vector. So we get a Hankel form that, we just saw the definition. And then we say that this Hankel form is PSD whenever the Hankel matrix constructed from the vector is a PSD matrix. Okay? So this matrix kind of depends on the coefficients of the polynomial, clearly, just like the catalectic matrix does. They may be similar. Let's see an example to really understand how if there's any link between them. So I had to choose a polynomial, which is this one is an abomination, but I felt like obligated to show it to you just so you know where the matrices come from, but just forget about it. We can construct the matrix, and I believe that you will happily trust me if I tell you that I did my homework. So these are the two matrices, and the first thing that we notice is that one is smaller than the other. That's not such an insane observation. But, they say that humans are good at pattern recognition. Does anybody want to make a guess maybe on how these two matrices are related? I can maybe let you see that, for example, the first 3x3 block is the same, both of them. Does anybody have a guess? Okay. I have a guess, luckily. And so if you really look closer and you put the indices, then you see that in this big matrix, some rows and columns are in fact equal. Okay, just look at the third column, the third row, and the fifth row. They look quite similar. Actually, they're the same. The same thing happens with the fourth one and the sixth one, and also the seventh and the eighth one. And the same happens for the columns, simply because the matrix is symmetric. Okay? And while in this matrix, kind of HP, what is happening is that we don't get the duplicate rows and columns. Okay, so at least in this case, HP is what we call a principal submatrix of CP. It's obtained from the other if you just get rid of some rows and columns. And when you get rid of, I don't know, like the ith row, you also need to get rid of the ith column. Okay? And maybe someone can ask himself, but how often does this happen? Very often. Actually, it happens always. It happens always. And the reason why is that, for example, you can see it by just introducing an equivalence relation that tells you that in the set of monomials, you just consider two monomials to be the same whenever they have the same weighted index sum. So this is kind of the natural equivalence relation induced by the Hankel structure. And in this way, you can also see the set of Hankel polynomials in some fixed degree and number of variables as a quotient vector space of the homogeneous polynomials. And in this case, HP is now the catalectica matrix of P with this new base consisting of the equivalence classes. Otherwise, you could also make some kind of substitution. So to xi, through the weighted index sum, we kind of associated a weight. And if you make this kind of substitution, then the weighted index sum of a term becomes the degree. And you can also see it using this univariate polynomial. There's many ways. But what I really want you to understand is that the matrix HP can be easily retrieved from the catalectica matrix, that it's super easy to find. And also, it will get some properties of the matrix CP. In particular, if we have a positive semi-definite matrix, all the principal submatrices are also PSD. Okay, now let's get back to the important theorem. So we have this decomposability, let's say, of PSD Hankel forms. And the sketch of the proof is really simple and, kind of beautiful, I would say. You just use the hamburger moment problem to the vector V. And because V kind of is a one-dimensional vector that encodes all the information of this multivariate polynomial. Okay? So the proof works even though you think of hamburger moment problem as some one-dimensional thing, while we're working with multivariate polynomials. And so we can draw this kind of Venn diagram, as we noticed before. We have non-negative polynomials. Inside of that, we can find SOS, sum of squares. Then there's also this sum of even powers of linear forms. And inside of that, the PSD Hankel polynomials. Unfortunately, this kind of set is quite small. The set of Hankel polynomials is a vector subspace, a strictly smaller vector subspace. And inside of that, the PSD Hankel polynomials form a cone. And you can easily find some examples that pretty much tell you that the inclusions are strict. For the first one, well, it's pretty well known that the PSD cone is in general bigger. There are polynomials that can be expressed as sum of squares, but not as sum of even powers and of linear forms. And I put you an example, but it's really not trivial to see this, so I'm not going to prove it. And finally, to build an example of a polynomial which is a sum of even powers of linear forms, you can easily just construct a polynomial which is not even a Hankel form. Okay. Now let's get back to the quadratic form CP that has not played a role in the presentation yet. What we can see is that whenever the polynomial P has a really specific structure, so in this case is a power of a linear form, A in this case is just a vector of k entries, then if you expand the expression of CP, then CP is a sum of is a square, and the coefficients of the square are strictly related to the entries of A. And this is a really important observation that helps us kind of link the composition of the first polynomial as a sum of powers of linear forms, and CP as a sum of squares. Because clearly this extends to sums. Okay, you just take a sum and the same proof holds. So we can now kind of combine these two ideas. Before I forget, this kind of observation also gives us that the minimal length of a representation of a polynomial as a sum of even powers of linear forms is bounded by the rank of the matrix CP. In fact, this length, this minimal length, is always greater or equal than the rank of the matrix. Okay, this gives us lots of information. Okay, now, amazing. Let's just combine the two concepts. So we can say that if we get a Hankel form and we ask not only the Hankel form to be a PSD Hankel, but we ask for the CP form to be a sum of squares, so the bigger matrix needs to be positive semi-definite, then, trivially, P is a sum of CP is a sum of squares. Sorry. We are assuming that CP is a sum of squares. Then what we get is that our starting polynomial is a sum of even powers of linear forms. And then there's this connection between the composition of CP as a sum of squares, where these are still the same multi-indices. This is a multi-index of length k, and that sums up to m, and a decomposition of P. Okay, so when I realized this, I was super happy. And since the proof is also quite simple, you just, from CP being a sum of squares, you get that the matrix is positive semi-definite, and then also the principal submatrices are positive semi-definite. So our starting polynomial is PSD Hankel, and it admits a representation. And then by the observation that we made before, we can just kind of link the two concepts. Yeah, so I was extremely happy. I couldn't wait to show you like an explicit decomposition of a polynomial. Unfortunately, in the following slides, there's no decomposition. And you may ask why. And the reason for that is that I kind of didn't realize that the sum of squares decomposition are of a very specific type. So if you take a look at these coefficients, not every sum of squares decomposition of CP will work. Actually, really specific ones. Only really specific ones will work. In fact, if you, for example, have that the AI's vectors are in some kind of set, then these new coefficients will lie in the image of the degree m Veronese, for example. But even though I cannot explicitly give you a decomposition using this theorem, what we can kind of take away from the corollary is that actually finding such decompositions is as hard as finding a decomposition of sums of two even powers of linear forms. And actually, like before this kind of result, I would have had no reason to believe that even like such a decomposition would exist among the many SOS decompositions. But this kind of tells us that they do indeed exist. Okay? And so many questions arise from this. First of all, I would like to find out if you can always find such a decomposition for a polynomial which is a sum of squares. I'm afraid not, but I have not thought about it yet. And many more. So first of all, I told you that the HP can also be seen like through a substitution with the powers of the one variable t. You can maybe think of instead of substituting just one variable, do a multivariate substitution. So from the starting polynomial, get another multivariate polynomial. And what happens then, we really don't know. Like, could be interesting to be investigated. Then as I stated the problem, we only tackle like kind of non or positively weighted sum of even powers decompositions. There's many people interested in weighted decompositions that not necessarily have a positive weight, okay? And finally, this kind of tells us something about decomposition in terms of powers of linear forms, but what about powers of higher degree forms? We still need to kind of think about it. And at the end, I left the references, and I thank you for your time.
Time for questions. I may have one to. Oh, okay.
Okay.
Yeah, so just to confirm that I'm not misunderstanding anything, but in general, like if you try to write a form as a sum of powers of, as a positively weighted sum of powers of linear forms, then that's basically the same thing as like you have a finitely supported measure and you want to reconstruct the atoms, right? Just by interpreting everything as a dual object.
Yeah.
So these problems should be like more or less equally difficult, right?
I think so. Yeah.
Yes. And now what you showed here is that like sometimes for these Hankel forms, you can, if you have like in addition this Hankel condition, then you can obtain these decompositions, right?
They do exist. Yeah, I can say that they do exist.
You can say that they do exist.
Exactly.
Have you thought what it means like from the perspective of like this measure reconstruction or polynomial optimization side?
So you're asking like how the Hankel condition, what role does it play in the measure setting?
If instead of your form you think of the moments of a measure, yes?
I didn't think of that, no. No, yeah.
Other questions? So I may have one at the end, your corollary. Can you show it back, please?
Sure. Okay.
So you say let P be a Hankel form, so it's a positive definite Hankel form.
Just a Hankel form.
Okay, but then you say if P is a sum of squares, so so that's a restriction you made on P, right?
Yes.
So what happens if you don't make this restriction? So suppose P is positive, and you want to know whether it has a decomposition. What happens?
So I suppose that P, what property? Just P is non-negative.
Non-negative.
Okay.
Is it easy to find the decomposition or to decide whether it exists? Some of
so I'm thinking.
Even powers of linear forms.
Shouldn't this be equivalent to CP being non-negative too? And so because P being non-negative, I can write it with the Gram matrix. And so CP is just a substitution of the monomials. And so I'm saying, equivalently, I'm saying that CP is non-negative.
Okay.
But since
so
CP
you're
is
saying that
equal to,
P non-negative is equivalent to CP non-negative? That's what you're saying?
I think so. I think it holds,
okay.
yes.
Okay.
And so, in particular, also this condition. So they should coincide, I think.
So if CP is non-negative but not a sum of squares, what can you do?
CP is degree 2.
So it's always a sum of squares?
Yes, if it's
so
negative.
if P is positive, the assumption that CP is a sum of squares is useless?
Yeah, exactly. It's an equivalence.
Okay.
It's an equivalent way to state it. Yes.
So you always have a decomposition of PSD Hankel forms then, under no condition?
Yeah, exactly.
Okay, good.
Thank you. Yes.
Other questions?
Yes, thank you.
Okay, if not, thanks again.
Thank you.